Okay, we're back for part two of the chapter 8 lecture of the Zelle third edition of the Python book. So if you missed part one, well, go play that and come back. Okay. So far, the two of our control structures that we have covered are if and while. And the point that we're making here on slide number 69 is that we could get by with them just fine. Okay. There are some programming languages that have more formal control structures than if and for and while. And languages like Python that essentially don't. But it's important for us to think of a class of problems that doesn't fit exactly into while. And so that's what we're going to do now. So we had, the while is a pre-test loop. Okay? It's a test before loop. Okay? Some languages have an explicit construct for a post-test or a test after loop. A lot of times it's called something like a do until. Okay? No equivalent in Python. But there are times when we want to set up a loop such that it kind of behaves like a post-test loop. Well, how so? Well, one important aspect of a pre-test loop, the while loop, is that it's very good at detecting situations where we don't want to do the body of the loop even once. Okay? And so it's really good for situations like you have a sequence you want to iterate over, like the empty string, okay, or the empty list, or the empty file, okay? Terrific, okay? But there's a whole group of problems in which you want to do the body of the loop at least once. And that would be, that's the reason why a lot of programming languages have a test after loop or a post-test loop in which you're guaranteed to execute the body of the loop at least one time. So we're going to explore that group of use cases, and we're going to talk about how we program for them in Python. So say we want to write a program that's supposed to get a non-negative number from the user. If the user types an incorrect input, the program asks for another value. The process continues until a valid value has been entered. This process is called input validation. So let's see. On the left, we've got the pseudocode. That's the modern way to model logic. On the right, we've got the programmer flowchart symbols. Kind of a clear way to visual things, but not really the modern way. So on the left, we say repeat, get a number from the user until number is greater than or equal to 0. So this is the classic until loop or test after loop. And as you can see it diagrammed on the right side, so we do the body and then we do the test. Test after, post-test, whatever you want to call it. Okay? So when the condition test comes after the body of the loop, it's called a post-test or test after loop. A post-test loop always executes the body of the code at least one time. And there's a whole class of problems that this is well suited to, okay? Python doesn't have a built-in statement to do this, but we can do it with a slightly modified while loop. Okay, so we just have one while loop. It's a pretest or a test before loop, but we can dress it up and have it behave like a test after loop, which is what we want. So we're exploring how to do that. So we seed the loop condition so that we're guaranteed to execute the loop at least once. So in here, it looks like the loop control variable is going to be number. So we say number equal -1. We assign -1 to number, and then we say while number less than 0, and then we say then we prompt for a float, enter a positive number. So we're sure to do it at least once because we seeded the variable. We cheated. We preloaded it with a value that meant that we're going to execute it at least one time. Okay, so that's one easy way to force at least one execution of the loop. All right? Some programmers prefer to simulate a post-test loop using the Python break statement. And this is a very popular approach and one that we'll do some exploration of. Executing the break statement causes Python to immediately exit the enclosing loop. Break is sometimes used to exit what looks like an infinite loop. So let's take a look at that. So here's the same algorithm implemented with a break. Okay, so the word break here is not part of the code, it's part of the slide. Okay, the code starts with while true. Okay, while true. Okay, well that's going to go forever. We saw that when I did my demonstrated infinite loop program. We say while true, and then we prompt for the number, enter a positive number, and then we say if x is greater than or equal to 0, break. So that's how we get out of the loop. Okay, what does break do? Well, it stops the iterations. Well, first of all, you don't finish the body of the loop, okay, and then you don't start the next iteration. Okay, you really break out of the loop structure completely and immediately. So a while loop continues as long as the expression evaluates to true. Since true always evaluates to true, it looks like an infinite loop. When the value of x is non-negative, the break statement executes, which terminates the loop. If the body of an if is only one line long, you can place it right after the colon. So let's go back and take a look at that. So we say if x greater than or equal to 0, break. Now, do I consider this to be good coding practice? I don't. Okay? So if you have a single line code block, I'd want to see it indented as a single line code block. Do you have to? Well, obviously no. We see that you don't. Is this good practice? It's not good practice because it doesn't visually signal to people reading the code that we have a code block here. Okay, that we have an if and then a conditional execution. So even though you can do this, it doesn't mean that you'd want to do it if you were on my team. Okay. So wouldn't it be nice if the program gave us a warning when the input was invalid? Yes, I think we would all agree that that would be nice. In the while loop version, this is awkward. Okay, so we preload number with a -1, and then we say while the number is less than 0, and then we go around if the number is less than 0, the number you entered was not positive. We're doing the validity checking in 2 places. Are we? Yeah, we're doing it here, and we're doing it up in the while. Okay, so it's kind of redundant code. All right, that's something that we're trying to promote. We'd like to write the code succinctly enough that we're not duplicating things unnecessarily. Adding the warning to the break version only adds an else. So again, we say while true, then we prompt, and then we say if x is greater than or equal to 0, break. That means that we've got a proper input. Else, we're going to print the number that you entered was not positive. So we're going to print a warning, and then we're going to go back up to the top of the loop and begin the body again, in which case we're going to prompt for positive. So this is, I think, prettier. Okay. Some people don't prefer this. This while true seems kind of brazen. Right? It's kind of saying, okay, I'm going to set this thing up to run forever, and then you're going to have to figure out how we're going to get out of it. There's a bold and brazen aspect of it that some people don't like. But this is a pretty popular and easily understood construct. So once you get past the boldness and the brazenness of it, I think it's just fine. Well, went too far. Stylistically, some programmers prefer the following approach. So they say while true, then they prompt, and then they say if x is greater than or equal 0, break, and then the print comes after the break instead of on an else. Now this is, I think, harder to understand, okay? But once it's explained to you, you'll get it. I probably like this less than the preceding one. When we encounter a break, we not only stop the iterations of the loop, we don't complete the body for the iteration that we're on. We really break right here in this one spot. It says break, we're gone. We go out of the while, and then we do whatever code is after the while, okay? So we don't do this print, okay? It's like having the print hanging off of an else, really, okay? So this kind of coding is kind of old school. It's kind of from the days of go-tos and such. But you'll find people who have coded this. So implicitly, we only execute the print if we haven't done the break. Whereas if you look at the prior version of it, it's pretty clear that we're either going to do the break or we're going to do the print. Okay, one or the other. I like this. I like this. It's kind of funny. 40 years ago, I would have liked version 2. But I think this is better documentation. Here on slide number 78, where we see either we're going to break or we're going to do the print. The fact that if we do the break, we're going to jump over the print, I don't think that's, that's true. I mean, that's the way the language works. But it doesn't stand out to me in the way that the version on slide number 78 does. Okay. Here the loop exit is in the middle of the loop body. This is what we mean by a loop and a half. Now, I'm sure some computer scientists talk about a loop and a half. I've been a programmer for 40 plus years. This is the first time I've ever heard the expression loop and a half. But probably there's a whole group of people who talk about it. That's because we're jumping out in the middle. Okay? This isn't as... a while ago, I think it was last chapter, I introduced you guys to this whole idea of structured programming. And in structured programming, it was said in the sort of original set of rules that we had, we said that every piece of code had only one entry and one exit. And typically, if you really wanted to be conservative, that exit was always at the bottom of that code. Now, this actually breaks that rule. So some really dyed-in-the-wool structured programming people would have not liked the use of the break. Okay? I think we've gotten past that. Okay? And if you... I think I had pointed you to a Wikipedia article on structured programming, and if you read down through that and click through on the sub-articles and stuff, you can see a discussion of, they discuss this in terms of, is a function allowed to have more than one return statement? And again, there are people who think that more than one return is a bad idea, and there are those who think it's completely okay. It's the same thing with the break. So, loop and a half, you'll have to take his word for it. I don't know about loop and a half. The loop and a half is an elegant way to avoid the priming read in a sentinel loop. So you say, while true, get next data item. If the item is the sentinel, break, and then process the item. So then, because of this, you can put your read at the top of the loop, which means you don't have to have a priming read up here. Okay. Now, I think what I like about this, one, what I don't like so much is you do have to jump out with a break, which is take some extra thought. But the other thing, having your read at the top of the loop instead of having one pre-read and then your loop and then your read at the bottom, that's a little bit non-intuitive. Okay, and this being able to do this so that your read is at the top of the loop. The cost is you have to jump out with a break. I don't think that's a bad trade-off. Okay? So I can't say that I do this a lot, but I know people who do. Okay, so this is the programmer flowchart for his loop and a half, as he calls it. So you can, at the top of the body of the loop, you can do your read. Then you check if it's the sentinel. If it is, you break. If not, you do the work of the body. Here's where you process the item. Okay, and that's a pretty good construct and fairly popular in Python. So to use or to not use the break, that is the question. It's a matter of style and taste. I mentioned just a minute ago that there are people who are kind of dyed-in-the-wool structured programmers who believe that the use of a break is not structured programming and that you should avoid it. I think their number has gone down substantially in the last 40 years or so. So I don't think you have a lot of people arguing that anymore. Although from time to time, if you get me wound up, I'll argue it myself. Avoid using break often within loops because the logic of the loop is hard to follow when there are multiple exits. Okay, and so one of the principles of structured programming was to say each piece of code should have one entry and one exit. Well, if you look at the code that we had here before, it has only a single exit. It exits from the middle of the code, but it only exits one time. So I think that that's a pretty good compromise. Okay, having code where you have multiple breaks within the code is more controversial and harder to understand. Okay, so Boolean expressions as decisions. So Boolean expressions can be used as control structures in themselves. To a certain extent, we have done the very simplest version of this in the loop that we've been experimenting with, where we say while true. Okay, we're using true to keep that thing just going around forever until we forcefully break out of it. Okay, so that's like kind of a structural use, a control structural use of the term true. Suppose you're writing a program that keeps going as long as the user enters a response that starts with the letter Y, like our long ago discarded version of the interactive loop. One way you could do it was to say while response index 0 equal Y, or Y while or response 0 equal uppercase Y. Okay, yeah, well, you could do that. We're checking for one or the other. All right. So be careful. We can't take shortcuts. Okay, so this is not equal this expression here, where response 0 equal Y or uppercase Y is not does not give you the same effect as the other way. Okay, why doesn't it work? Well, Python has a bool type that it internally uses 1 or 0 to represent true and false, respectively. The Python condition operators like equal always evaluate to a type of bool. However, Python won't let you evaluate any built-in data type as a Boolean. Now, this is a kind of an interesting cheating and it leads to that code up there meaning something different than you think. For numbers, int, float, and long ints, 0 is considered to be false. Anything else is considered to be true. So if we, so the way to get the Boolean evaluation of any kind of object is to call the function a bool and pass it that object. So bool of the int 0 is false. Bool of the int 1 is true. Bool of the int 32 is true. So 0 is false. All positive values are true. Bool of the string hello is true. Bool of the empty string is false. Okay. Bool of the list 1, 2, 3 is true. Bool of the empty list is false. So you kind of get the hang of when we evaluate non-Boolean objects with Boolean logic. Each of these non-Booleans has a way that it translates into a true or a false. And essentially, 0 or empty is false, and 1 or full is true. Okay? So an empty sequence is interpreted as false, while any non-empty sequence is taken to mean true. The Boolean operators have operational definitions that make them useful for other purposes. Okay. So Boolean expressions as decisions. So x and y. If x is false, return x. Otherwise, return y. X or y. If x is true, return x. Otherwise, return y. Not x. If x is false, return true. Otherwise, return false. Okay. Now, for me, all right, I would rather see sort of the Python version of the code on the right rather than the Python version of the code on the left. The fact that these things are equivalent is interesting, but I don't think it makes them good, readable code. These are coding tricks that are probably best not used. So consider x and y. In order for this to be true, both x and y must be true. As soon as one of them is found to be false, we know the expression as a whole is false, and we don't need to finish evaluating the rest of the expression. Okay, so this is an important principle that can help you quite a bit. So the Python end is only going to evaluate the left part if it finds a false on the left part, because it's as soon as it knows that x is false, it doesn't care what y is, and is going to be false. And it does a similar thing for ors. And this these logical operators, and we'll see this in just a minute, are said to be cutoff operators, where it cuts off the processing as soon as it knows the answer for sure. So there are times when we want to take advantage of the fact that that the logical operators are cutoff operators, and I'll show you that in a minute. Okay, so it says as soon as one of them is found to be false, we know the expression as a whole is false. And we don't need to finish evaluating the expression. So if x is false, Python should return a false result, namely x. If x is true, then whether the expression as a whole is true or false, it depends on the y, the right side. By returning the y, if y is true, then true is returned. If y is false, then false is returned. Okay, now this is kind of shortcut code thinking. Okay, again, I'm not sure that leaving this kind of code behind for other people to read and understand is really the best thing to do. Probably better to have more explicit code that's easier to read. These definitions show that Python's Booleans are short circuit operators, meaning that a true or false is returned as soon as the result is known. In an AND, where the first expression is false, or in an OR, where the first expression is true, Python will not evaluate the second expression. Okay, now this turns out to be important. There are times when we want to evaluate some input that's come from the user. And first of all, we want to check if it's a proper input. And then if it's a proper input, we want to convert the value. And if we check if it's a proper input, if we check that it's a proper int or a proper we check that it's a proper int or float or Boolean or whatever we're trying to get in. If we check that on the left side, then the expression on the right side can rely on it being proper. Okay, and that turns out to be pragmatically helpful in some particularly web validation and processing code. Okay, so to get back to the code, response index 0 equal y or y. The Boolean operator is combining two operations. Here's an equivalent expression. Response index 0 equal y or y. By the operational description of or, this expression turns either true if the response was equal to lowercase y or uppercase y, both of which are interpreted by Python as true. So when you take a string and you give it a logical evaluation, if it's not empty, it's going to be true. Okay, so this is always going to be true, right? So if you check if the response index 0 equal lowercase y or uppercase y, it's always going to be true because uppercase y evaluated from a Boolean point of view is always going to be true because it's a string and it's longer than the empty string. Sometimes we write programs that prompt for information but offer a default value obtained by simply pressing enter. Since the string used by ants, so I guess that ants is the variable where we're going to store the string that we get. Since it can be treated as a Boolean, the code can be further simplified. So we say, yeah, turns out that ants is the variable. So we can say this. We could say input, what flavor of you want? I think we want, what flavor do you want? And this is, I think, indicating that vanilla is the default. And then we say, if ants, flavor equals ants, else flavor equal vanilla. Okay? So, again, the empty string is going to evaluate to false. Okay? So if we say if ants, with this is equivalent to saying if ants not equal the empty string, then the flavor is going to be whatever we got in. Else, the flavor, if it was equal to the empty string, the flavor is going to be equal to the default. Okay? If the user just hits enter, ants will be an empty string, which Python interprets as false. We can code this even more succinctly. We can say ants equals input, and then we have the prompt with the indication that there's a default. And then we say flavor equals ants or vanilla. So if ants is the empty string, that's going to be false. Then it's going to take the default. If ants was a proper value, then it's going to take that value instead of the default. Okay? Remember, a non-empty answer is interpreted as true. So a non-empty string is considered to be true. This exercise could be boiled down to a single line. So we could say flavor equals, and then we do the prompt, or vanilla. Okay? So if in fact the user inputs a proper string, then we use that. Otherwise, we use the string vanilla. Okay? Now this is a common kind of Python coding trick, and it's a little bit obscure. Okay, but it's used enough that it's something that you ought to know. All right? So that's why we teach it. Again, if you understand the method, feel free to utilize it. Just make sure that if your code is tricky, that it's well documented. So I'd say this qualifies as having been tricky. Okay, to the uninitiated Python programmer, this I think is tricky. Okay, now here's what I want to point out. Is this version at the bottom of slide 95? Is it particularly faster than the version on the top? And I don't think it's a lot faster if it is faster. So you don't have to be kind of bullied into these really terse coding tricks like this one that's at the bottom of slide 95 in favor of over things that are at the top of slide 95. Okay? Or even more deliberate versions like this. All right? This looks even better. Okay, so the fact is that before our code is executed, it is interpreted. It's sort of compiled into this stuff called P code. Okay, and it's a P code that gets interpreted at execution time. So the question is, the P code that gets generated by the version on slide 94, is it drastically different than the version at the top of slide 95 or the bottom? And I'm going to go out on a limb here and say that the P code for all three of those is pretty much identical. Okay. And so one of them is probably not any faster than the next. And if it is, it's very small. Okay. So I'm going to really encourage you to code in a way that's explicit and easy to read. I want to make sure that you're able to read code like this. For instance, code that's as tricky as the code on the bottom of slide 95. But if you're not committed to being this tricky of a coder yourself, that's just fine. I mean, there's a certain school that says that this code on slide 94 is better code. Why? Because it's easier to read. Okay. Now, there are plenty of Python people who would say, well, that's kind of baby code. And they might say that something like we see at the bottom of slide 95 is more Pythonic. Well, not everyone agrees. Okay. Okay, so the end of this chapter is based upon things in a graphical user interface. So it's using classes from chapter 4, which we skipped. Okay, and we're not going to cover slide number 97 through the end because of the fact that it's based upon something that we didn't actually cover. So we're going to let that go. So I'm going to stop here, and I'm going to wish you good luck on your homework exercises, and I'll see you again next time. Bye-bye.